Thank you very much for taking the time today to view our video. Before we begin, we'd like to take a moment to introduce ourselves. There are many aspects to 9.Connects, but it boils down to the fact that we're a PCB-centric organization. We believe and focus on the PCB due to the fact that it is truly the center point of all electronic design. That's where our expertise lies. We provide services not only in the PCB layout, but in design consulting as well. And during the technical portion of this webinar, you will see this expertise in motion. We are now the exclusive North American instructors for Altium Designer. We host 100 trainings throughout the year across North America, and we are excited to bring these trainings closer to you. In addition to our services, we are also a value-added reseller for a number of PCB-related software companies. And just to note, each company has been presented in past webinars. So if you're interested in them, please contact us or check out our website. And by the way, we provide one-on-one coaching for these tools as well. For more information on our services and past webinars, please contact us. Our information is listed in the description below. Thank you for giving us a moment of your time, and please enjoy the presentation.
I'm going to give a very brief introduction to the concept of manufacturing files. And the reason I want to do this is that the conversation we're going to have today with our two guest speakers, David Hoover and for Rayfugit, they're going to go into a lot more detail about the issues with these files. However, what we have found with a lot of PCB designers, they don't really understand what these manufacturing files are all about. So I'd like to spend a couple of minutes talking about that today, and then we'll hand it over to them so they can go into more detail. The biggest problem that we have, quite frankly, is being designers, and this is the issue I've always had with it, we always kind of threw it over the wall. We threw it to the purchasers to deal with it. We sent it to the manufacturers directly. Well, what do we really give into the manufacturer? And so that's what we're going to kind of explore here for a couple of minutes today. And then we're going to talk about the major formats in the manufacturing files. They're basically their main formats and their capabilities. All right, just wait for this to come up here. So let's talk about the processes. I wanted to put this out here so that we can understand what we're trying to get to. We all know this process over here. It's the PCB layout. But what are we trying to do when we're throwing those files on over to the other side? What's manufacturing doing with those files? Well, when we provide them either the Gerbers or the ODB Plus or even this newer format called the IPC 2581, we're giving them instruction sets to ultimately get to what's called the photolithography. All right, and in certain instances, they may even do a validation on those, depending on the manufacturer. Now, some of the fast turn guys, the high volume guys, really aren't going to do this at this point in time. There's a number of different manufacturers out there. Some of them, they just provide, hey, high volume, you guys have already done this, you know your stuff, just give it to us, and boom, we'll start pumping them out. Other people are very fast turn, like PCB 123, they'll try to turn it in 24 hours. But what you give them is what you're going to get. They're not going to run any validation on it to make sure that there's no manufacturing issues on those. All right, and so you do want to talk to your manufacturer about that, or better yet, you should take control of these. And that's kind of what the theme of this is today, is we're trying to show you what goes on beyond Altium Designer or any of the other EDA tools, and then how can you control it so that when you talk to your manufacturer, they're all set to go, and that there isn't this kind of hope and pray type of aspect of it that what you provided them actually works. Okay. So once you've got through validation, if you do it, and I do encourage you to do it, we have to do something called a photo plot. And the best way to understand a photo plot is think of it as an old-fashioned transparency. So if you've ever done presentations in high school or in college or maybe your early years in your engineering career, before we had the laptops with the projectors connected to them, we had a transparency, which was basically a clear sheet with information on it. We put it on a light table, right? It was just called a projector, and we project those onto the wall. Well, that's pretty much what a photo plot is. It's just in this case over here, it's acting like a template, and we're going to use this as a part of our photolithography process, which is really the first major manufacturing step in making a printed circuit board. I make this one comment over here about the LDI. What is LDI all about? Why do we care? Because LDI is this thing called laser direct imaging, and with this, it actually skips over this particular aspect of the process. And this is actually huge because photo plotting's been around since the 1950s. So we're taking a process that's been around for well over 50 years, and we're basically going from your information straight into the equipment that does the photolithography. Well, let's talk about photolithography for a minute, because if you don't understand what we're saying over here, it's not going to make a whole lot of sense. This is the general process that is going on in the manufacturing. The first two over here are ones you don't even have to worry about. This is what the manufacturer does even before your boards come in. boards are usually created with a laminate and an insulator and another piece of copper, pardon me, it's copper, an insulation, and another copper. This could be FR4, it could be core, depending on what it is, but it's all prefabbed. And these usually come in 18 by 24-inch sheets, again, to fit the manufacturer's equipment. Now, what they'll do is they're going to apply something called photoresist on top of this, and that's so that we can get an image onto the copper. Right after that, you've got a photo plot, or basically this transparency, which you can place on top of it. Or if you've got the LDI, it's going to basically use the laser image, and it's going to use this process in which it exposes it to light, and through a chemical process, it's going to start making a chemical change to the copper. And once that's done over here, then you basically remove your artwork, like your photo plot here, and then you go through several chemical processes where you basically remove the copper you don't need, and that's what ultimately is going to come of it. But obviously, in order for any of this stuff to work or even go forward, you've got to have a clean photo plot. You've got to have clean files for this to work, right? And then from there, it's just the rest of the manufacturing process to get your basically your electronic design into reality, into actual copper. And just to give you another aspect of it, this over here just says the same thing as before, but this is an actual piece of equipment here. Now, this piece of equipment does use a photo plot. You see he's actually picking up the photo plot right now. Again, it's clear plastic with the information on it. This actually just finished its process. So he pulled it out. Basically, this piece here slides in and out of this piece of equipment, and this plate is pulled up. And then what he would do at this point is he's going to take this piece of transparency, or the photo plot, he's going to take it off, and then he's going to remove the copper, and the information or the stuff that you want to keep has been etched into, or actually the area that you want to preserve has been etched into this area over here onto the copper. That piece of copper is now going to be taken off to another machine where now they're going to remove the photoresist and any of the copper that had been exposed to the UV light. Okay, so that's the process that we're trying to get our files into over here, and that's done for every single layer. Okay, so that gives you a general idea of what we're trying to do with those files. Let's talk about the files themselves, and there's really two major formats out there. There are the Gerbers and there's the ODB Plus. Now, there's also the IPC 2581. Let me talk about that for a moment. That really has a basis in ODB Plus. And the reason for the 2581 was that the IPC, which a lot of people should be familiar with, they create various standards for the entire industry. And the biggest problem with Gerbers and ODB Plus is that they are owned by companies. Gerbers is owned by a company called UCAMCO, and ODB Plus is actually owned by Mentor Graphics. And both those companies, since they own it, they make it open source. At any time, they can pull it back and say, no, this is now proprietary, and that has a lot of people on edge, both on the EDA side of things and in the manufacturing side of things. So IPC came together with, in particular, Cadence and Zukin, and they said, okay, let's deal with this, and other people have signed on to this. So there is now this thing called IPC 2581. It came out basically in 2010, and in 2012 they proved it out. But in terms of, since it's very rarely used at this point, it's just so introductory, I think you can think of this side here as the ODB Plus as also being the 2581, because the 2581 has its grounds or its basis in ODB Plus format. So let's talk about these two formats. So Gerbers, we've all heard this term Gerbers. Why do they call it Gerbers? Because of Gerber Scientific. As a company that was created in the 1960s, and they made these photo plotters. And I didn't have time to go into the history of this, but those photo plotters were the ones that were basically creating those clear plastic sheets that would be ultimately placed over the copper for the photolithography. So they were keen on that. In the 1980s, they actually created the RS 274 standard, which is better known as the Gerber files, or the Gerber standard. Okay? And from that point on, that's how the name stuck with it. They create one file per layer, and so if you're using something like Altium Designer and these other tools, you'll create those things. You can create them out of any of the layers in Altium. It can be a mechanical layer, it can be your silk screens, it can be the actual copper layers. You can throw pretty much all of those over to the manufacturer. They're pretty good about knowing which one's which, but you should certainly also provide them stack ups so that you know which files to use. The ODB Plus actually uses a file directory system. So instead of dealing with things on just strictly a layer basis, they kind of break down things into different categories, things like artwork, the drill files, even the bill of materials, even the net list as well. I'll talk about this over here because it's good and it's bad, and you have to decide which works best for you here. But the key thing I want to talk about right now is this thing called the .tgz file, and it's kind of a humorous aspect of the ODB Plus. because people think that you have to provide a .tgz file in order to use ODB++. Now, Altium Designer does not do that. But .tgz is not specific to ODB++. It's actually a remnant from Unix. So you got to keep in mind that when Valor created ODB++, they did it in Unix. They also did it for Cadence, Allegro, and some of the earlier tools for Mentor Graphics. All those tools used to reside in a Unix platform. So why do they call it .tgz? Because in the old days, not to date myself over here, but if you were going to send a cassette or a CD over to your manufacturer because the internet just couldn't handle the bandwidth to send them over through FTP or these large files, you actually sent them a physical media. And in order to get this onto the media, you basically had to stream the information on. And you had to do it kind of in one shot. You couldn't say, well, I'm going to send this file, and I'm going to send this other file in this other directory, and I'm going to send this other one yet in another directory, because the media couldn't handle that. So you had to do something called the tar function. And the tar function was this thing to take all these files that I'm pointing to and make it one large file. And in fact, the end result would be this thing called the .tar file. Now, that's not compressed. It's just one large file. But to get it to fit onto the tape or the CD, they needed to compress it. And a company called, well, actually it's not a company. It was maybe a consortium or an open source group called, it's GNU, actually. It's not GUN. A lot of people call it GUN, but it's actually GNU. And they had this command called GNU zip. And if you ran this over on the file, in the .tar file, you would actually get this thing called .tgz. Because if you ran GNU zip on just to a file, you get a .gz file. But if it was already tarred, it was smart enough to know that it would actually give you the TGZ, which stood for tar gun zip, or pardon me, tar GNU zip. Actually, I looked that up today. It's not GUN, it's GNU, according to the founders of the GNU program. So that's where the .tgz came from. It was just to tar it and to compile it all together. The only reason I bring that up and go on to that tangent is that when I worked for Altium, we get calls all the time from customers and a panic saying, my manufacturer can't use my ODB++ files because you're not putting it in this format. And I have to call the manufacturer and tell them, no, you just got to point it to the directory after you unzip it. It's fine. But they got really panicky if they didn't see this particular extension. But that's what the extension's all about for those people who are not familiar with Unix. All right, let me get on over here to Gerbers versus ODB++. Gerbers are really simple. And I don't mean this as a derogatory thing, but they're really stupid. And that's actually a good thing, because all they do is tell you where the copper is supposed to be. And that is it. ODB++ shows you everything, or it can show you everything if it adheres to it. For you Unix, or pardon me, Altium users out there, Altium will only provide enough information to get you through manufacturing. It will not get you to the assembly side. Okay, so the assembly side, for example, there would be stuff like the bill of materials over here and your pick and place stuff. Gerbers do not contain that particular information. All right, let me talk about the claims. What does Gerber claims? Well, over 90% of the PCBs made in the market today are using the Gerber format. ODB++ claims an 80% efficiency over Gerbers. That's what I've read on the internet. Talk to your manufacturer and see if that's true or not. Everybody has different equipment. You'll have to see if they actually gain something over that. Those Altium Designer users, you can create either Gerbers or ODB++. In terms of getting the source, if you're ever curious about it, you can actually get the source information. So you can get the Gerber information from UCAMCO's site. Who is UCAMCO, you're probably asking yourself? Well, instead of giving you 3 slides on this, UCAMCO is what was Gerber Scientific through various mergers, acquisitions, and name changes. All right, so UCAMCO's site, www.ucamco.com, you can go there, get the download. It's a 200-page PDF on the Gerber format if you're ever curious about it. For ODB++, this was created by a company called Valor. You may have heard that tool before. Got purchased by Mentor Graphics back in 2010. And when Mentor obtained ODB++ for a period of time, they actually pulled it away and made it proprietary, and that ruffled a lot of feathers in the industry. And as a result, that's why the IPC 2581 came about. But Mentor relented, and they actually made it available for anybody. If you're interested in that format, go on to the site over here, www.odb-sa.com. You will have to create a login. It's free of charge, and then from there you can get the download. The last thing is, what about concerns? Why should you use Gerbers, or why should you use ODB++? With the Gerbers, you got to know what you're sending. And the biggest problem that I think happens with most people is that they send a bunch of Gerbers. They don't realize that they may be missing something because the Gerbers are actually very limited. And so you got to make sure that you provide everything to the manufacturer, that you understand the manufacturing process. Otherwise, you could be delayed. Where if you maybe sent it over a weekend, good, we got the files out. Come Monday morning, you find out they didn't do anything because you forgot to send them 2 or 3 additional files that they needed. And again, Gerbers are only for fabrication. They are not for assembly. They have no pick-and-place information in them. They have no component information in them. They are strictly for the fabrication of the board. ODB++, other than the fact that there's always some concern about the format being pulled back as being proprietary, the biggest concern with it is about reverse engineering. So the idea with ODB++ many years ago is that instead of someone having to know what to send to the manufacturer, if you created the ODB++, it was all there, it was all complete. You sent to the manufacturer and or assembly house, and boom, you're done. With a lot of stuff going overseas, this could be dangerous because if you're sending it to a company that's not reputable, they can quickly reverse engineer your stuff, and now your intellectual property may be stolen or duplicated. So just be aware of this. As I mentioned earlier, for those people using Altium will only create enough ODB++ information to do the fabrication. It will not do the assembly. I don't know about Cadence and Mentor if they provide additional capabilities to withhold information here, but just be aware of that if you're going to send it to a company that you're not familiar with. Of course, if you're working with a company that you've worked with for many years, you know they're reputable, then ODB++ may be the easiest thing for you to do. That's all I've got about this at this point in time. I wish I can go into a lot more detail. This slide deck has another 10 slides about the history of photo plotting. It also has the history of the 2 formats for Gerber and ODB++. They're both very fascinating, and they're kind of good to know because then you can see where the industry is going with stuff. If you're interested in that slide deck, at the end we will put up the information for your local sales rep. Please do contact them, and we'll make those slides available to you. At this point in time, I'd like to introduce to you David Hoover. So David is with TTM Technologies in San Jose, California, and he is a senior applications engineer. He's got well over 35 years experience in the PCB industry, and he's very active with the IPC and several of their subcommittees. And so he's going to be presenting some of the issues that they see in the manufacturing area. And at this point in time, I am going to turn the presentation over to him. So give me a moment here while we switch out the screens. All right, David, feel free to jump on. We can do a quick sound check if you'd like to.
Sure, I think I'm in here.
Yep, it looks like you're in, and I see your screen, and I hear your voice just fine. You're on.
Great, super. Okay. So, yeah, thanks for Paul for passing that along. Today I'm going to talk a little bit about DFM and DFX and some of the different things we do on the PCB fabrication side. But first I want to talk a little bit about some of the acronyms that are out there. I think the first time I ever encountered some of the involvement was with some of the Selectron and some of their other folks. They came up with an approach called DFX, DFX being a variable. You know, and that I think they also called it design for excellence is another term that I've heard over the years. This includes many things. I think we hear the term DFM, and it really incorporates a whole bunch of different things. On the PCB fab side, we're really doing something that is a subset of DFM. Think of DFM like the big umbrella. And we do something called DFF, and DFF is designed for fabrication. But it also incorporates many different things like DFE for environment, DFA for assembly, DFR for reliability, you know, and DFT, of course, and of course the fabrication side of things. So when we do a design review, it's always good to have a lot of folks involved. When they review that design, and especially me on the fabrication side, I always try to make sure the assembler is involved because I get a lot of folks that ask for arrays or, you know, suggestions and this or that affects the actual assembly. So I want to make sure that the assembler is involved, yet we also keep the project headed for, you know, high volume manufacturing. And so let's see, we have design for reliability and design for environment. The other thing is rework. Rework always comes into play. So, you know, we got to make sure that the parts in the design is also good for rework for the assembler. So is that enough 3-letter abbreviations? It gets very confusing. And There will be a test at the end of this, so I hope you're taking notes. Okay, so let's start out with the first thing when the data comes through for the DFM. Your fabricator typically does something called a design rule check. And what it is it's an automated, script-driven process that typically only applies to Gerber, ODB++, and the data as it's coming in. And it's kind of a 2D review. It really considers parameters individually, and it doesn't really consider combined effects. And usually on the fabrication side, it's a CAM operator, computer-aided manufacturing, where they basically are running this automated script process. So beyond that is where it kind of gets into the higher level, where we're really doing a more intensive DFF, right, for fab, and it involves a higher level review. And what it does is it reviews the process from the data that's fed in from the DRC, and it looks at cumulative effects that come into play with such as parameters and tolerances, many different things in that design, including the PCB stack-up, enhancements for improved reliability to make sure that the yields are kept high and reduces the amount of scrap. So manufacturability is a big concern. And again, the assembler really needs to be involved for like panelization and assembly direction and some of the different things like that. And usually that's done by a higher level person, such as a pre-cam person or a senior engineer or a DFM engineer or an FAE like myself. And it's always good to get these folks involved early on as supplier involvement. So let's look at some of the different things that come into play on the top level on DFM waivers deviations. And keep in mind that well over 2/3 of what I see come in, as far as new designs, there is some sort of waivers or deviation requests right up front. So what I've done is I kind of sorted these out into the electronic data side of things, and then also into the manufacturing side of things on the second set. So I guess the first thing would be an incomplete fab package, and we'll go into more detail in a few slides exactly what that is. And then some basic stuff, rudiment, like part number, revision level doesn't match the PO, or the prints, or the data, stuff like that. We got to make sure that all the revisions match, and versions and whatnot, all has to go along with what the PO says. And then I think the next one would be fab print versus the Gerber data. And I think a lot of times fab prints will have adjustments, and maybe the Gerber data didn't incorporate that, or vice versa. But it's always good to have the two match, and if they don't, someone's going to stop the job and ask to have that clarified. And then net list violations, if they're known, they should be listed in the README file or on the fab drawing. Otherwise, we have a net list violation, and we're going to ask questions right up front. Things related to the stack-up, such as line widths, where in this case I'm mentioning singlet and differential are laid out on the same line width. It doesn't really give your fabricator the ability to adjust those independently and maintain the impedance requirements for the targets between both the singleted and the differential. We do a global edit, and if they're not independent, we don't have that flexibility to adjust them independently. And then also impedance trace is not identified. This would be like on a print where it says, controlled impedance 50 ohms, and we're scratching our head going, well, which line widths? There's maybe 4 different line widths identified in the design itself. Array drawing needs to be created and approved. This is another thing where, we see quite a few requests on that, and I strongly recommend this is the one that gets the assembler involved, because there's so many things that come into play. Overhanging components, for example, breakaway tabs. Do they have a equipment that can cut them apart? The pizza cutter for V-score. I mean, all these different things. The assembler really has a lot of input on that. And then another one that seems to be on the rise, and that's with regards to back drilling. And we'll have some more information on this on a couple slides back, but a lot of good things to talk about here is that this is probably one of the largest things that we get, is where we get the job in, it talks about back drill, but the back drill files are missing. And so when I talk to a lot of the engineers, their layout tool, they're actually, it's done after the fact, and either they don't push the button, or they don't run the script, or whatever they do, they're just not they're not there, and they're not supplied. So we always have to push back and say, hey, we need the back drill files, because they're just not contained in the package. or they're not identified, and that could be a bunch of different things. But you know, this is a thing that we see pretty routinely. Now, moving on into, I want to say, the DFF, or the manufacturability side of things. So this would be where your fabricator would see an issue, and they really are now making a request for modification. And this would be like in the back drill continuing on, where the violations are the cut or must not cut's not specified, where we're going to have to go in and ask what those layers are and then put them in our stack up. So that way we know what depth the back drill is going to go to, and it's going to have a must cut or a must not cut layer specified. And then also what is, like, for example, the via stub length. You know, these are things that we have to ask for. So on that back drill, that's the amount of via that's left remaining past the must not cut layer. And then also back drill to metal. So it's a concern, and I have a slide that shows this pretty good, especially on BGAs, where if you come in with a back drill, you're real worried about the distance of copper around it. And folks in North America versus folks in Asia may have a little bit different capabilities or you know, tolerances that they live with, so they may ask for different criteria. I know that a lot of the OEMs here, Tier 1 OEMs here in the United States, ask for, you know, 7 mils. That's probably something that they want to live with, and they know that in the field it has, you know, some sort of long, reliable length and time. But, you know, some of these BGAs, you just can't get there from here. And I got some slides, like I said, coming up, and we can talk some more about that. Other issues are like non-plated holes hitting copper, solder masks not being specified or being specified incorrectly, or the fabricator has different capabilities. So clarifying all that up front gets to be a little bit of an exciting discussion. Solder mask webs based on capabilities. So some fabricators can, you know, do a certain amount of solder mask web between BGA pads. And then also removal of non-functional pads. So this is kind of an interesting subject, because depending on really where your camp is, whether I know that the military folks like to leave them in, and digital commercial guys like to pull them out. And on the fabrication side, we like to pull them out. And the reason being is, you know, it's harder to drill through copper than it is through fiberglass. And so if you only have the pads that are necessary in there, it has, you know, a longer tool life on your drilling process, not to mention that every piece of copper is a pixel on the AOI machine. So if the more copper you have, the longer it takes to scan the layers. And so, you know, by having those non-functionals removed, it actually speeds up the AOI process. And AOI is automatic optical inspection. That's kind of an interlayer inspectional process. And then the last one is really talking, on this page anyways, talking a little bit about, you know, CNC routing, the routing of the outer perimeter of the part. They like to have some of the values where they're, you know, the copper is a certain distance or more. A little bit more, this is definitely something for a data enhancement on the manufacturability side from the fabricator. And this is the addition of teardrops, and that's, you know, the pad to the trace junction. They'd like to have this teardrop added. In this case, it's a fillet. Could be a double flash or a snowman type, and that has to do with registration of the drilled hole. And that's to maintain criteria for the annular ring. And that goes into this next item where, depending on the requirements of the part, you could have Class 3, Class 2 IPC requirements. Each one has a different annular ring requirement. And it requires an adjustment to the pad size to incorporate the proper target for the annular ring. And the other thing that comes into play is the copper weight. The heavier the copper weight, the more etch compensation we have to do on the fab side, or the larger the pad needs to be to achieve and maintain the target annular ring. Next item would be like hole tolerance sizes, vias. Typically vias, you know, you're not going to put a wire in there. And so we always ask for like +3 minus the via nominal value. And the reason for that is if you're drilling with a real small drill and you have a big, big, thick board, you have the possibility of something known as drill splay or drill wander. And if you're trying to put a pin gauge down in there, you can't put a pin gauge in with wander. So it suggests the hole size is a lot smaller than it really is. And if you've got a tolerance on that via, and it's like ±3, and I can't get a pin gauge in there, we're going to end up scrapping out a board that's perfectly good electrically. Press fit drilled hole sizes. This is a big issue that we see, where the press fit folks, connector folks, will be supplying a drilled hole size with a finished hole size and tolerance, and in many cases it's not manufacturable by the fabricator. And again, it has to do also, it plays into this, the capabilities of the fabricator versus the actual part itself. The thicker the board is, the harder it is to plate, and the harder it is to plate a very level hole to meet press fit hole requirements. So all that stuff has to be taken into consideration up front. Otherwise, it's kind of too late in the game if the parts are built and they don't meet the spec. Hole to copper violations, this is just in general. This is a 3D thing, so this is not like, you know, your DRC catching this. You're going to have to be looking at that hole going all the way down through each and every one of those layers, and can it meet the plated through hole to copper distance or the non-plated through hole to copper distance. Both of these are taken into consideration. Next item talks about something called copper thieving. This is adding copper squares in a broken up pattern or in a solid, depending on the part requirements, but like a solid copper that's applied for plating purposes or for thickness distribution. And so this kind of equates to better uniformity across the panel, which really helps the overall yield, including the impedance requirements or the impedance findings across that whole trace within a given layer. Some of the other items that are also important during the DFM stage in consideration is something known as copper wrap. And I don't have a slide on this. I wish I did. This really is a reliability requirement that has to do with the size of copper around the knee of the hole at the tops on the knees of the holes. So as certain products come into play, such as epoxy filled plated over, that copper wrap's important because folks are afraid that when they go through the assembly process, if the copper wrap is too small, it'll snap off, kind of like a butt joint, and it could come up as an open after assembly. Other capability concerns that we see is like such as slots, the length and width being below minimum, such as plated through slot. It's easier for us to hold the width than it is the length, and in some cases we ask for plus or minus 5 or plus or minus 4 mils on the length and plus or minus 3 on the width for a plated through slot. And it's just important to know that it all has to do with how those are manufactured and the abilities of the plating. Next item is slivers on planes. So typically we'd like to clean those up if they're 3 mils or below. And the reason is we don't want them to fly off somewhere else in the process and land somewhere where they don't belong and create either a short, or in the case of outer layers, it'll have a pinhole that goes right through either a trace or a copper area. Another item causes the DFM to slow down is the pre-approved stack-up doesn't match the requirements in the data. And typically, if there's a pre-approved stack-up, those line widths that are determined and agreed upon really should be applied for the layout process. And sometimes adjustments come into play. And of course, if the stack-up doesn't match it, we're going to have to go back and try to figure out, you know, how to incorporate the proper sizes and stuff. So these are really the top items that kind of, I want to say they're showstoppers, but, you know, really these are the items we got to work through on the DFM process and sit down with the OEM and engineer, design engineer, and kind of go through all these. And sometimes in signal integrity or hardware folks get involved. We've got to make sure that everybody agrees in the direction to go. So some of the things, how can you avoid these errors in your PCB design process? I guess the first thing we talked about was the design package. You know, try to supply a complete design package. That incorporates all of the things shown here, and we talked a little bit earlier about ODB Plus. I mean, there's a lot of different formats that we can take, including the 2581 and the ODB Plus. You know, but again, supplying all the proper information, the net list, the README file, the drawings. We kind of like to have the solder paste files at TTM, and the reason for that is it tells us where the test points are going to be located because they get solder pasted. Or if you have a solder mask and solder paste files supplied, we're going to check the two against each other, and if they don't jive, we're going to raise a flag and say, hey, something might have been overlooked here. We're not experts, but we just kind of want to use a second set of eyes and take a look at that. And then if there's any other types of files necessary, such as solder mask plugging, selective gold masking, any of those types of things, you got to always make sure that those are also supplied. So we talked a little bit about annular ring. Annular ring is where we have a violation of a pad size to a drilled hole size. We just got to make sure that the pad size meets the requirements of the reliability of the printed circuit board. You know, what exactly is necessary. And so these are the things that pop up during the DFF stage. The hole to copper violations, this, you know, is like especially in the case of planes, many times we'll see clearances in ground planes where they're just not laid out, they're too small, they don't meet the requirements for a given, you know, product requirements. Also, you know, it may be easy to have a prototype shop build maybe 5 or 6 NPI units, but man, when they have to go to offshore or wherever to have tens or hundreds of thousands of parts built, it's a different game. The requirements there need to be a little bit more conservative. I mean, it's easy to kind of build 20 units and have 5 that work out really fine, but man, when you got to build 10,000 of these things, you know, it's perceived quite a bit differently. Adding of copper thieving, and all this really is you take a layer or an outer layer, inner layer or outer layer, and you have some areas that have a lower copper density area compared to other areas that have a higher copper density area, and you add a certain percentage of copper dots, in this case, they're dots, and you bring up the uniformity of that layer. And in this case, you might have the same amount of percentage of the thieving area as it is to where the traces are. And this is really, really good for prepreg yield on the inner layers, because if you have controlled impedance traces, you're going to have less variation along the entirety of that length by doing something like this. If there's any epoxy filled and plated over, and there's any sanding that takes place on those layers by the fabricator, by doing this to the inner layers, they have less variation and more uniformity, hence better results and higher yields. So that's kind of how that comes into play. Back drilling, we talked about the issues with the files missing and where it's necessary to specify the must cut and must not cut layers, and then also the via stub length. Here's a couple graphics that show you kind of the way how it works. You take a plated through hole, and it's pretty much finished, processed out through. And then on the finished board, we'll come in with a controlled depth drilling process and drill down and produce a back drilled hole. So the via has a stub that's reduced in length past you know, a given layer. So electrically, they don't have a bunch of energy being robbed going out beyond the actual interconnect. The interconnect may come in and shoot across the layer, and then you have this given stub length. And the length of that stub length is typically determined by 2 things. The electrical requirements determined by the length set up by the OEM, and then also the fab shop's capabilities. And some shops may be able to do better than others. It all depends on, you know, where you're sitting these parts out that procure them. Let's see, and then I talked about back drill to copper distance. So that would be like here, this distance right here. It's a big concern. If these planes are closer to this back drill, or they hit the back drill and you have exposed copper, electrically you may not have a problem right now. But in the field, if you're inside of a server closet somewhere on the equator and you've got 80% humidity and, you know, fans going and it's really hot in there, if this plane was really close down here at the bottom, you could get some sort of a fungal growth and maybe electrical chemical migration shooting across there, where it would develop into a short. And they've actually had some documented cases where this has happened. So the process for back drilling, of course, you take a printed circuit board and you control depth down to a given distance. And in doing that, what you do is you determine that stub length. Now, sometimes it's kind of difficult to determine if you've got the proper via stub length left. And a lot of times it's a destructive test. We'll actually take one board and we will go out and do cross sections and measure those things physically to make sure that we meet the stub length. Our industry right now is in the process of running some tests electrically using some pretty high-end frequency domain equipment to measure those distances, those stubs. And in the future, we should have some way to test those things and determine what the stub length is electrically. So on BGAs, this is where back drilling really gets tricky. In the case of a 1 millimeter pitch BGA, you've got 4 mil lines, 4 mil spaces, 2 track going through there. You can see that some of these back drills are actually going to cut and clip into these traces. On a plane layer with a clearance, an anti-pad at 28 mils, you know, you've got a distance really, really small. It's like just over 5 mils. And then on signals, it's very, very tight. So these are all the concerns that we look at when we do the DFF, trying to figure out what the capabilities are. We also have to look at the OEM specs to see what their criteria is. And in some cases, some OEMs are required to have the back drills filled with epoxy if they're less than a certain value. Same with 0.8 millimeter pitch. Pretty much the same criteria comes into play. You know, and it's a challenge, and we're seeing more and more and more of this as the high-speed digital guys come into play, and they're all out racing to try to get to 25G. So, you know, it's a challenge, and they want that stub length reduced and very, very small. Solder mask approach, we talked about that. It's always good to talk with your fabricator and make sure they explain exactly what they want. And also on the design side, that the requirements are exactly specified so folks know. This is a good graphical representation to kind of pass between people, and that way they get an understanding. I want it to look like number 2, or I want it to look like number 3, and things like that, because there's a lot of different terminology also that's used throughout the industry, depending on what part of the globe you're in, so we don't always use the same terminology. Good clean stack up, have it all clear right up front. That's a big plus. That specifies both single-ended and differential, and the same line widths are not applied for both. That's very important. And then one of the things I wanted to talk about that I see more and more and more is, you know, everybody wants lower loss materials. FR4 took us to a certain level and got us where we wanted to go for many, many decades, but now they're all saying they want signal loss. They want a reduction. They want it to go down. Problem is the material cost goes up. So I just want to make sure folks realize there's a lot of trade-offs, you know, trying to get to the really, really low loss materials. It really is not a cheap material. It really drives the PCB unit price right up through the roof. So these are the types of things that I see. I see it day in and day out, and TTM is a very large fabricator and a player in the game, you know, and so we see this kind of stuff routinely. Okay, so with that, I think I can give the ball over to someone else. That's the end of my presentation, and thank you, everybody.
All right, thank you very much, David. We're going to switch over the presenter here to Ray. Ray, I'm going to make you the presenter, and as you're setting up over here, let me just give a quick introduction. So Rayfugit is with the Downstream Technologies. He is one of their senior field applications engineers. For Downstream, they have 2 products. One of them is the DFM stream, which he's going to demonstrate today, and the other one's the Blueprint. Ray's got 20 years experience in the EDA industry, and he'll also be at PCB West along with David. So I'd like to introduce to you Rayfugit.
Thank you, Paul. Just a sound check and a screen check.
Yep, see your screen, hear you just fine.
Okay, I've got a DFM stream up on the screen right now. What I'd like to do in the time left here is kind of reiterate a few points that Dave made and then just give you a quick overview of our tool here. One of the things that Dave said is just kind of aside from what we're talking about here today, or it goes in with what we're talking about, is get the application engineer involved early in the process. So if your fabricator has a Dave, then get them involved and they can really help you with the design, and the earlier the better. Our tool kind of goes right along with that in that, you know, you may not be using a large manufacturer, you may be doing prototypes. And a lot of the time they don't have tools that can do the analysis to catch the items that Dave spoke of earlier. So what's needed is a tool that can find those types of issues, whether you're working with someone like Dave or just working with a prototype shop, so that you can fix those issues before you send the designs off. Okay, we don't have the multiple spins of the design. Dave mentioned a couple things here that I'd just like to, that I wrote down as he was talking, I'd like to talk about. And one of them is like different capabilities depending on which shop you're using. So that's when you're using a tool to do analysis, you should have the flexibility to have different parameters in there. He mentioned Asia versus the US. He also mentioned IPC classes. These all have different requirements. Okay, if you think about the IPC, they have different requirements from layer to layer. All right. He also mentioned, and I'm just going to quickly do it, one of the issues aside from DFM was the whole idea of creating array drawings. As Paul mentioned, we have another tool that is set. The purpose of the tool is for designers to create array drawings. It's not for a CAM operator. It's for designers to do it, and it's made to work through wizards so that you can quickly create array drawings, as you see here on the screen. Okay. So when we start talking about the DFM tool, though, it should be flexible, it should be powerful, and it should have tools to help you validate the issues once you run an analysis. Okay? Let's just think about it for a second. If you've got a typical board that has 5,000 or 10,000 holes on it, just one failure is 5,000 or 10,000 failures. For a lot of people, that's what makes them throw their hands up in the air and say, oh, I can't run analysis. I've got 10, 15, 20,000 errors. So the tool should be able to look at those errors in groups. So I like to say that the whole concept of running DFF is not just how long it takes to actually run the software. It's how much setup do you have to do, how long the software takes to run the analysis, and then how much validation you have to do on the back end. What kind of tools does it provide to help you? So this is our tool here. This is DFM Stream. And you can see it's a checklist-based analysis that we're doing here. Okay? And in this particular one, I brought in a generic one, and I can have many different generic analysis, again, based on fabricator, IPC class, technology, however I want to break them down, and I'll show you how you set that in just a second. But to this, what I did is I had a BGA here on my bottom layer, as you can see. So I wanted to do a particular analysis just in this area. So this is another thing that your DFF tool should be able to do, is to be able to define areas and run differing analysis on your designs based on the areas. So then again, in this case, I want to validate my constraints here in the BGA area, and then I want to run a different set of analysis on the rest of the design. So the CAM tool, the DFM tool, should have the flexibility to do that. And you can see that I've split off my bottom layer from my BGA area, and I'll run differing analysis with different parameters on each. And then we've got, obviously, the other types of layers, and the analysis is broken down into layer type. And if you look at, one type of layer versus another, you'll see different types of analysis that are run. So on a signal layer, for instance, I've got about 45 different types of analysis, everything from different types of copper spacing, if that's important to me, and it is to a lot of people, to checking copper to routes, internal routes or external routes, or checking back drill to copper, as Dave spoke of. So I should be able to do all those types of analysis on my design, and then if I run a different type of analysis, let's say paste mask, for instance, I have checks that are specific for paste masks. Okay, I'm even doing ratios or making sure I have fiducials, things that are more geared towards assembly that maybe than fabrication. But you should have the power to be able to run these types of analysis in your tool. Okay, so the setup, as I mentioned before, you can have as many different, we call them streams, as you want. And in these streams, you know, depending on the customer that you're using or depending on the fab shop you're using, you just bring that one in and run against a design. You shouldn't have to recreate it each time. So you probably noticed when I was in here and I was on any of these, you'll see some values in here. This is the other part. There are other very expensive tools out here that I can't just do something as simple as change that value from 10 to 9 without going to an external tool. It should be easy to use when you are running DFM. Okay? Again, I mentioned the areas and the being able to validate constraints by areas. That's very important. And then the results when you do run analysis. Okay, so you shouldn't get, for lack of a better way of saying it, freaked out by 3,600 errors because, you know, it might be, as in this case, that, okay, 359 of them, if I chart them, I find out, well, I've got 3.5 mil annular ring on my vias. Now, again, as a designer, you know, that may be what you intended, but your fabricator is going to go, and you know this, can we teardrop them? Well, put it on a print. Let them know ahead of time. So that's one less communication that has to go back and forth. This is not a showstopper, but it's something that, you know, you would have to have that communication. And if your fabricator's in Asia, there's the day to answer that question. So charting really helps. You can select, and it'll show them all to you. You can say delete them, and you've validated all those issues with 2 or 3 mouse clicks without having to go through each individual error, which is often the case. You know, I hear that, you know, designers will say my CAD tool has analysis built into it, and usually when there's errors, I have to walk through each one individually. Okay, and other things that Dave mentioned, like through hole to copper, we've got some errors there. I'm not going to go through each one of them just for brevity here, but again, you know, things like solder mask to track, making sure we don't expose traces. We even split it up into 2 different ideas if you want, to copper fills or to traces, and you may have different values for both, or you may have the same value, or something like this where you have masked slivers. And again, I can go ahead and chart the masked slivers, and immediately I know that it's the dams in between these surface mounts. So again, if I really need those dams, I have to first of all find a fabricator that can hold whatever that number is. 2.1, that's going to be a stretch, I think. But second of all, I might just say, go ahead and make these into, we call it a window pane or a block clearance or something like that. Again, if I can say that up front, less back and forth between me and the fabricator. So this is the main purpose of running DFF ahead of time, is answering some of these questions before they're asked. So again, there's less back and forth between you and the AE, which again, as I said, you should get involved in your process. But again, if anything you can answer ahead of time really helps you in the long run.